We do have a couple of equations that we can use because we do want to be able to calculate some of these predictions. If I know my temperature is going to, if my temperature goes up, my volume is going to go up. I want to be able to calculate that. So we have several different formulas, but if you can just think about it in terms of the combined gas law, then that's going to make it a lot easier to remember. So you don't have to memorize this formula, but we are going to practice using it several times. One thing that you want to note is that temperature must always be in Kelvin. The reason why is because Kelvin is a unit of measurement that doesn't have any negative numbers. The lowest number you can get is 0, or technically it's almost 0. So it's not going to mess up our calculations, because if we're using an equation that has a fraction, if we have a negative number, that's going to mess up our proportions. So we always want to make sure that we're converting our Kelvin or our Celsius into Kelvin, and we can do that with this formula right here. So we're really just going to add 273.15 to any Celsius number. Okay, and again, you won't have to memorize these numbers. You'll be given them, but you need to know how to use them. So let's look at a couple of examples, and I'll show you a few tricks. Okay, so to get started, the first thing I'm going to do is just write down my formula. And then now I'm going to look through my question and see what I'm looking at. So first things first, I'm given 22.5 liters. I know that liters is a unit of volume, which basically means my first volume is 22.5. The next number that's given to me is 748 millimeters mercury. I know that millimeters mercury is a unit of pressure, so this is going to be my pressure measurement. The reason I wrote them as V1 and P1 is because these are my starting amounts. I'm told that I have 22.5 liters of nitrogen, and it's at 748 millimeters mercury. So that's the volume and the pressure. Now it's telling me that I'm going to change that. I'm going to compress or push in this space, right? So that now the pressure is at 725 millimeters mercury. So essentially it's just telling me that I'm going to lower the pressure. Okay, that's all compressed means. This is the second time, though, I'm given pressure, so I'm going to write it as P2. So 725. And then it's asking me, what is the new volume? So I don't know that second measurement. So the V2, that's going to be like my X value. That's what I'm going to be solving for. So if I come back and look at my formula, I'm given a V1 and a P1. I know the P2, and I'm solving for the V2. But what I don't have any information on is temperature. So what I'm actually going to do is I'm just going to erase this part of the formula. So what that means is I do not even need to put temperature in this equation because temperature is not changing. So now all I have to do is just plug in my numbers. So I'm going to start here with the P1. So that is just 748. V1 is 22.5. P2 is 725. And V2 is X. Now I know that I just need to multiply my numbers that are next to each other together. And I get a pretty big number. And this is still the same over here. I haven't done anything to the right side yet, but I know that if I need to get X by itself, that means I need to divide by 725. I have to do that to both sides. And so my answer is 23.214 And then this is volume that I'm solving for, which I know has to be liters because this is liters right here. So this answer is not in significant figures. I can put it in significant figures. I know that this number has 3, this number has 3, and this number has 3. So that means my answer has to have 3. So here are my 3 significant figures. So 23.2 liters. If significant figures are still confusing to you, then just ignore that for right now. What I really want you to focus on is solving our equations. Let's look at number 2. Okay, the first thing I'm going to do is I'm going to go through, I'm first going to write down my formula. So again, I'm always starting with the combined gas law. That's a 2. And then I'm just going to go through and look and see what are all of my numbers. So I'm given 4 liters. That's going to be a volume. I'm given a pressure. And I'm given a volume. And then I'm asked to solve for the pressure, final pressure. So my V1 is 4.0 and my P1 is 205. kPa, or kilopascals, is just another unit of pressure. My V2, it tells me my new volume is 12, and I'm trying to solve for pressure, which is X. So again, I'm given a P1, a V1, a P2. I'm given a V2, and I'm solving for P2, right? My P2 value is the X value. I don't have any information on temperature. It's being held constant, so I'm just going to totally delete that out of my formula. Now I can just plug in all of my numbers. So my P1 is 4.0. That's my volume one. My P1 is 205. My P2 is the X, and then the V2 is the 12.0. So again, I can just multiply these two numbers together. I didn't do anything to the right side yet, but I know that I need to divide by 12 so that I can get the X by itself. And when I do that, I get 68.333, just repeating, right? That's my X, which really X is the P2. So my pressure is 68.333. Now let's look at sig figs. I have 2 here. Yes, that 0 is significant because, yes, there's a decimal. I have 3 right here and 3 right here. So 2 is my least sig fig. So that means I have to stop my answer at the 68. Now, if I'm asked for units, since I'm solving for pressure, the pressure units given to me in the problem are kPa. Again, if sig figs is confusing, just skip it for now. We really just want to solve the equations. So I'm starting again with my combined gas law. I'm going to go through and read my problem. It tells me that I want to calculate the temperature when I have 6 liters at 20 degrees Celsius. It tells me the volume is changed or decreased, right? Remember, compressed just means lowered to 4. And then I'm looking for the temperature. That's what I'm trying to solve. So I'm told that the first number I'm given, right, is my volume, which is 6. And then my first temperature is 20. My second volume is 4. And that's what it's wanting me to calculate, that final temperature. So I can get ready to plug all of this in. But before I do, remember I have Kelvin here, or I have Celsius. I need Kelvin here because I have temperature. So remember, the way that I get that is I just need to add 273.15. So I end up with 293.15. That's my new temperature that I want to plug into my equation. So I'm told a volume. I'm told a starting temperature. So I'm sorry, that should be a T1, not a T2. I got a little ahead of myself there. So I have a starting temperature and I have a final volume, and I'm calculating that final temperature, right? That's my X value that I'm looking for. Nowhere in this problem does it talk about pressure, which means I'm just going to essentially erase the pressure out of my equation. Oh my goodness gracious. So I'm going to erase the pressure all the way out, so I don't have to worry about it at all. So now all I have to do is just plug in my formula. So V1 is 6. T1, remember, is 293 because I converted it. V2 is 4. And then T2 is the X. The easiest way to solve this is to cross multiply. So we'll do a little refresher. It doesn't matter which way you go first, but it's all going to end up the same. So I'm going to multiply the 6 times the X. I'll keep it in red so you can kind of see. So I multiply the 6 times the X, and then I'm multiplying the 293 times the 4. And then now we're back to a basic equation that we can solve. So I know I need to multiply these two numbers together. And again, it's probably going to be a bigger number, which is okay. So I'm multiplying those two numbers together. And then I still have the 6x over here. I haven't done anything to that yet. But now I know I need to divide by 6 in order to get the x by itself. So I end up with 195.4 and then a bunch of 3's. So let's go look at our significant figures, okay? So we have 3, 3, and 3. So I'm looking at the significant figures from my starting problem because those were the measurements that I was taking. Those are what I want to base my significant figures off of. So there's just 3. So that means 195. And this is temperature that I'm solving for. So that means my unit has to be Kelvin because temperature is always in Kelvin for our gas laws. We're going to look at one more here. So again, I'm always starting with my combined gas law. I'm going to go through and highlight all my numbers or underline all of my numbers or write them down, right? Because that's what's important. So it tells me that I have a pressure and I have another pressure, right? So right here, right off the bat, I have my P1 and my P2. Then it tells me the volume went from 85 to 350. So again, right away, I have the V1 and the V2. It says, what would the final temperature be if the original temperature was 90? So that means I'm looking for the final temperature. So this is my T1. I'm looking for the final temperature, the T2. Don't forget though, with my T1, right now it's 90, but I have to remember to add 273 because I need it to be in Kelvin. I cannot use the 90 because that's Celsius. So all I have to do is add 273. So this is my new temperature that I want to use. So now let's just plug everything in, or kind of take a look at everything. In this one, I have a P1 and a P2. I have a V1 and a V2. And I have a T1 and a T2. So in this problem, I'm not going to erase anything out of my formula. I have to use this entire equation to solve this, because I'm looking at all three variables. So I'm going to go through and start plugging things in. So I have here's my P1 and V1, right? So that's the first things I want to write down. 85 and 1200. And then I have a T1, right, which is this 363. Now I can move on. I have a V2 and a P2. So I'm going to write those down just like they are in the problem. And then remember, my T2 is my X value. That's what I'm looking for in this problem. So again, we're going to cross multiply. So I'm going to multiply like this. So I have to do the 85 times the 1200 times the X. So I end up with 102,000X. Now I have to do this way, cross this way. 363.15 times 350.0 times 850.0. This is a big number. 108037125. Okay, so I'll write these numbers in. Okay, once again, let me just write it over so everybody can follow along. The first thing I did was I said 85 times 1200 times X, right? Let me do it this way. That's how I ended up with this number right here. 102,000 times X. The next step was to multiply this way. So I had 363.15 times 350 times 850. That's how I ended up with this big number down here. Right? I've got to get X by itself, so I'm going to divide by what's in front. So my X value ends up being 1,059.1875. So let's look at my significant figures here. Right here I have 1, 2, 3, 4, 5. I have 4 right here. 3, 4, and 3. All those zeros are significant because they all have a decimal. So my least significant figure is 3, which is right here. So that means this 9 has to round the 5 to a 6, and then I can just put a 0 so that my place values are the same, but I'm not going to put a decimal because I don't want that 0 to count. And then since we're talking about temperature, we're going to say this is Kelvin. This is where we'll stop for these calculations. We'll do more practice as we continue to talk about gas laws. If you need to go back and watch any of these again, feel free, or you can ask questions in class.